We're very happy to have Zhang here from Penn talking about 8D string universality and non-simply connected gauge groups. So.
Okay, thanks, John, for the introduction. And hello, everyone. I'm Zhang. I'm a grad student from University of Pennsylvania. And let me first thank John and Cody for putting up this great seminar series and for giving me the opportunity to present here. So today, the topic of my presentation will be 8D string universality and non-simply connected gauge group. So it'll be based on the work that came out last month I did in collaboration with Miriam Cvetic, Marcus Dirijo, and Ling Lin. So let's get started. So this is a roadmap of my talk today. So in the first part, I would like to set up our main goal of string universality. And in particular, I would give some background to that, and then explain why I would like to focus on 8D theories with non-simply connected gauge groups. So let me begin by some introduction of string universality. The statement of the string universality conjecture says that all consistent theories of quantum gravity should come as low energy limits of string theory. And let me give the classic case in 10D, which is in 10D n equals to 1 supergravities. From the local anomaly perspective, there are 4 apparently consistent theories listed here. However, only the first 2 are realized as gauge groups in heterotic string theories, whereas a long-time puzzle is that the last 2 theories are neither realized in string theory nor ruled out. So a solution to this puzzle finally came a long time afterwards, which states that the last 2 theories are found inconsistent via the following approaches that are independent of string theory. So namely, first in 2010, there's a paper by Adams, DeWolf, and Taylor used supersymmetry techniques and Abelian gauge invariance considerations to show the inconsistency of the last 2 theories. And also recently, there's a paper by Kim, Xu, and Vafa last year stated that showed that by unitarity bound, the rank of 10D gauge group has to be no more than 16, therefore ruling out the last 2 theories with huge ranks. Finally, as a recent progress in 8D, there's a paper by Montero and Vafa that came out last month. And part of their conclusion is that 8D supergravity theories needs to have rank 18, 10, or 2. And their result explains the long-known modular 8 pattern in the 8D string vacua with some techniques in involving the trivial cobordism conjecture that does not refer to string theory explicitly. Okay. So now let me also give some backgrounds about global structure of gauge group, which is another main theme of our talk, of our research, and explain why we care about this. So at the standard model level, there's a known ambiguity of the global structure of the standard model gauge group. So it can be SU3 cross SU2 cross U1 mod Zn, where any value of n coming from 1, 2, 3, or 6 is compatible with all of the LHC measurements. So as an example of what is the effect of global structure of gauge groups, let's compare the SU2 theory with an with an SO3 theory, which is also known as the SU2 mod Z2 theory. So the difference can be seen at the level of allowed representation. So for example, the fundamental 2-dimensional representation of the SU2 theory is forbidden in the SO3 theory. And in general, all of the half-integer spin representation of SU2 is forbidden in the SO3 theory. And such a difference is also visible at the level of non-local operators. So an example of that being the Wilson lines or toothed lines. So for example, all of the allowed Wilson line charges of the SU2 theory are present, whereas this is not the case for the SO3 theory. Okay, so the reason why we focus on 8D theories is that 8D string vacua has been known to exhibit intricate patterns in terms of its global gauge group structure. Namely, not all of the naively possible choice of global structure of gauge groups are allowed. And such a pattern can also be understood in terms of F theory via arithmetic structure of the elliptically fibered K3s, which will be the main approach that we look at from the string theory side. So in the following parts, we are going to first connect to the F theory arithmetic properties in part 2, and then independently connect to the higher form symmetries and mixed anomalies in part 3. And after that, we're going to compare this approach and lead to our goal of AD string universality, towards AD string universality. So now let me come to part 2, the string theory, and in particular F theory part. So one motivation that one cares about F theory in particular is that it is conjecturally believed that all of the F theory AD vacua can be realized. All of the string theory AD vacua can be realized in F theory in one way or another. So let me begin by giving some backgrounds of F theory. So F theory is the strong coupling version of type 2B superstring theory, with the SL2D duality geometrized as a torus vibration. And a classical description of F theory AD vacua involves having 24 PQ7 branes of each of specific PQ types locating on the base P1. And in addition, the overall monodromy of the 24 PQ7 branes has to be identity. Also, from the elliptically fibered K3 perspective, the gauge group can be read out via the Kodaira's classification. So generically, one has 24 I1 fibers, while collision of these I1 fibers gives the enhancement of the ADE Kodaira singularity type, which is read out as the enhancement of the gauge group. And now let me move on to say more details about where the discrete sector, the global structure information, sits in the F theory geometry. So to do that, we need to introduce the concept of Mordell-Weil group of an elliptic fibration. So the Mordell-Weil group of an elliptic fibration at a set level consists of all of its rational global sections, whereas the addition law is the fiber-wise addition law of cubic curves for two sections. And so as drawn in the figure, there's a zero section that I depicted in blue. And other than that, there are, if there are other sections as I draw in red, they would correspond to non-trivial generators of the Mordell-Weil group. While the zero section corresponds to the trivial generator of the Mordell-Weil group, consisting of the mark point at infinity for each fiber extended over the base. Okay. So since this addition law is also known to be abelian, therefore the Mordell-Weil group as a finitely generated abelian group admits the following decomposition into a free part and a torsional part. So each free section, i.e. each free generator of the Mordell-Weil group, gives a U1 gauge symmetry. And also, at the presence of another non-Abelian gauge vector, there is a joint quotient of the form G non-Abelian cross U1 mod center of G. Yeah, according to a paper by Miriam and Ling. And also, our main focus today will be the torsional section. So we know that each L torsional section would, in addition, gives a ZL global quotient. So these have been investigated in the papers like in 98 by Aspinwall and Morrison, and also later by Meyerhofer, Morrison, Till, Weigand, and recently by Hajoji and Oyelman. Okay. So now let's move on to some refined geometric or arithmetic properties in the elliptic K3s. So there's a paper by Shimada in 2000 that gave a complete list of classification of elliptically fibered K3s. So each element in this classification was marked by an ADE fiber type and also a specific choice of Mordell-Weil torsion, and there are more than 1,000 cases. So the Mordell-Weil torsion can either be a cyclic factor Zn of order up to 8, or a product of two cyclic factors with particular allowed combinations of the orders. And now we would like to look at even more refined data of given the gauge group global structure is G mod like either one torsional section, either one torsional factor or two torsional factors, we would like to see how is the particular embedding of this global quotient into the center of the simply connected gauge group G is realized, and also how can it be read off from the geometry. So to do that, we have to investigate how the torsional section, as depicted in red, intersects each fiber component. So there's a particular case that admits really nice and clean properties, which is the case of purely IN fibers corresponding to pure SUN gauge groups, or pure SUN gauge algebras. So an IN fiber has resolved components that intersect in the form of a cycle, which is also the affine Dynkin diagram of AN Lie algebra. So out of these Ni components of a INI fiber, there is one that is marked that is intersected by the zero section, which is conventionally referred to as the affine node. So we normally count the number of these components from the affine node. And now if I'm interested about how does this red L torsional section intersect each singular locus, we would get the number which is labeled as K sub I here. So it's counted from the affine node all the way up to here. And naively, one might think that the L torsional section at each singular locus can just intersect each resolved fiber component as its own wish, corresponding to arbitrary possible embeddings of G mod a cyclic vector Z sub K. But soon we will see that this is not true. And the F-theory geometry imposes subtle constraints on how this embedding is realized via particular ways of how the L torsional section behaves. Okay. So arithmetic constraints on the global quotient. So to repeat what I stated on the last page, for K3, the only IN fibers and a single L torsional section. So that is a restriction to a case we're considering that has pretty nice properties. The global gauge group is direct products of all of the SUNI factors mod a ZL quotient. But this is not everything. We need to know the specific embedding. So the embedding is specified by counting what is the image of a ZL generator into each SUNI component. So it's labeled by a tuple of Ki all the way up to Ks, and Ki, like out of which Ki is an integer modulo Ni. So this is the precise generator that ZL embedded into the overall centered Z of the semi-simple G. And this data is precisely encoded in the geometry in a way that Ki, for example, a K sub I here is precisely the number of resolved components that is intersected by this ZL torsional section, which is shown in the papers that talks about Mordell-Weil torsion in the context of F theory. Okay, so there turns out to be a non-trivial constraint to these Ki's. It basically says that each IN singular loci would give rise to locus would give rise to such a fractional contribution, which is Ni minus 1 divided by 2 Ni times Ki squared, where Ki is the number of the intersected component as counting from the affine component, and Ni is the order of that I sub Ni fiber. And it says that this fractional component has to sum up to be an integer, which is a highly non-trivial condition. And now let me give an example. So according to the Shimada classification, there's only one model with Z7 torsion, which is SU7 cubed mod Z7. And according to this constraint, the embedding of K1, K2, K3 equals to 1, 2, 3 can be verified to follow this condition. Therefore, this is an allowed intersection pattern. However, the equal embedding of K1, K2, K3 all equals to 1 can be checked to not satisfy this condition. Therefore, that is not an allowed embedding pattern. So by looking at the refined structures of F-theory arithmetic, we have obtained some constraints from how what is the allowed global quotient on the F-theory vacuum gauge groups and how is it embedded into the joint center. But now the question from the string universality perspective is that, do we have any field theoretic reason that can realize a similar pattern in a way that does not refer to string theory? So that is going to be a question that I'm going to answer in section 3, where I look into higher form symmetries and mixed anomalies and attempt to reproduce the patterns that I saw in F-theory geometry. So to begin, let me give some general backgrounds about higher form global symmetry. So in the classic paper by Gaiotto, Kapustin, Seiberg, and Willett, the concept of Q-form global symmetry was proposed to be a symmetry that charges operators of dimension Q. And also for Q greater than or equal to 1, the symmetry groups has to be abelian groups. And our conventional global symmetry will be referred to as a zero-form symmetry in their context. So in our paper, we focus on a particular class called center higher form symmetry, which we will give 2 examples below. So first of all, a continuous example is that in a 4D U1 Maxwell gauge theory, there is an electric one-form global U1 symmetry whose charged objects are the Wilson lines. And as you might have heard of, there's also a magnetic symmetry, a magnetic U1 symmetry charting the tooth lines, but we ignore them for the purpose of our talk, of our research. So I would also like to give a discrete example, which is in a 4D SUN gauge theory, there is a centered ZN valued one-form electric global symmetry charting the discrete Wilson lines. And that will be our main focus today. Good. So now let me talk about gauging one-form global symmetry. The reason we're interested in this is because we're going to move on to supergravity theories. And there, the one-form global symmetry has to be either broken or gauged. And today we're interested in the case that they're gauged for the reason that we'll explain soon. So for G gauge theories, without any matter charged under a particular subgroup gamma of the center Z, it can be shown to have a gamma valued one-form global symmetry. And one need to do the following things in order to gauge this symmetry, this one-form global symmetry. First of all, one have to couple it to a 2-form gamma valued background field, let's denote it by C. So by doing this coupling, the one-form center symmetry is reduced from Z to Z mod gamma. And after that, one have to then sum over all possible C configurations in the particular function. And doing this would give rise to a G mod gamma partition function in the 0-form sector. So in other words, gauging a subgroup of the one-form global symmetry or the entire one-form global symmetry would introduce a gamma quotient in the 0-form sector, which can also be interpreted as twisting the G bundle into a G mod gamma bundle with a non-trivial gamma valued second Stiefel-Whitney class. So if the last sentence doesn't make much sense, then it would be totally sufficient to understand the statement in terms of a quotient on the 0-form symmetry. Cool. So now let's look at a crucial mixed anomaly in 4D field theories involving this CN one-form symmetry, which we will then take it and generalize it to 8D. So according to a paper by Cordova, Fried, Lam, and Seiberg, in 4D Mills theories, there is a mixed anomaly between the one-form global symmetry and the theta periodicity of 2 pi. So to be concrete, let's take the instanton coupling of I theta over 8 pi squared times integral of trace f wedge f. And let's do a one-form symmetry transformation, and simultaneously theta goes to theta plus 2 pi transformation. And then there will be an anomaly term that pops out, which reads 2 pi I times alpha g of the integral of the Pontryagin square. So there are 2 quantities that I will explain one by one in the rest of this slide. First of all, the alpha G is a fractional group theory constant that depends on the particular choice of gauge group G. For example, for SUN gauge group, alpha G equals to n-1 divided by 2n. And it's worked out analogously for other gauge groups in those papers. And the script P of C is called the Pontryagin squared of element in the second cohomology class. So what matters more for us is that it is an integral element of the fourth cohomology, which does not spoil the invariance of the joint transformation. So in other words, the fractional part only comes from the alpha G, and that's why I label it in red. And to give more intuition about the Pontryagin square, if we promote the integral value C into a differential form, then the Pontryagin square can be roughly thought of as C wedge C. So that produces a 4 form. And okay, now I think we're ready to take the idea and move on to 8D. So to do that, we have to first, or one way is to first find the analog of the theta term, of the theta coefficient. So in 8D n=1 supergravity theories, the gravity multiplets contains a 2-form field B2, according to the textbook by Salam and Susskind. And this B2 field can also be dualized to a 4-form field B4 in a dual description done in the Awada and Townsend paper. And like in particular, this B4 has the following coupling term. So now we're assuming that we have a semi-simple gauge group that can be written into a product of simple factors. So for each simple factor, Gi, the coupling gives the B4 term, wedge product, the instanton contribution of this, of the gauge group of this Gi, which is written as 1/2 trace of Fy wedge Fi. And then I sum over all these simple factors. So now we're interested in the case with non-trivial quotients in the global gauge group, meaning there should be a gauged subgroup of the overall center Z of G. And as we have explained, to gauge it, we have to couple it to one 2-form symmetry for each simple factor. So as denoted here to be C superscript I, and which is valued in the center of Gi. So each such factor would give rise to an instanton contribution, which is alpha of Gi times the Pontryagin squared of this center 2-form gauge field C superscript I. And I sum it over all simple factors, and I only care about the mod Z component because it arises as an anomaly phase. So then I also do the shift as an analog of the theta 2-pi periodicity, which is B4 goes to B4 plus lowercase b4, where the lowercase b4 is an integral period field. And this would give us the following anomaly term, mod Z. So now comes the crucial point of arguing why this anomaly is a real constraint. So let me mention in passing that in 6D theories, there is also an analogous anomaly coming from a Green-Schwarz term, as done in a paper by Fabio, Marcus, and Ling recently. So let me reproduce the anomaly that I got in the previous page here. So the point of only writing alpha sub Gi in red is that this is the only term that could potentially be fractional, whereas everything else are integral. So according to a paper by Cordova and Omori last year, such a mixed anomaly cannot be canceled. And also according to a paper, the same paper by Fabio, Marcus, and Ling, such an anomaly, if it is fractional, it would give rise to a fractional electric B4 charge, which is not consistent. So this anomaly must vanish on its own modular integer, meaning that all of the simple factors of this semi-simple gauge group has to conspire to reach a cancellation of these fractional coefficients. So now, as an interesting subcase, let's again look at the case with only SUN gauge groups. And now, same as beginning, we assume that we have a gauged cyclic ZL factor with a ZL value 2 form field C. And now to characterize how this C field embeds into each centers of the simple factors, we set C superscript I equal to K superscript I times C, with Ki being an integer modulo Ni. So it says that, or this notation means that the ZL quotient is generated by the element of the same tuple Ki all the way to K1 all the way to K sub S in the overall center of the semi-simple group. Then the above constraint, equation 9, would translate into this familiarly looking integral constraint, which says sigma of Ni minus 1 divided by 2Ni times these factors Ki squared should be an integer. And one might recall that this is exactly the same constraint as the arithmetic condition for elliptic K3s with only in singularities. So now we have indeed answered the question that we raised at the end of section 2 by deriving the same constraint observed in string theory geometry with a way that does not refer to string theory. And okay, now let me proceed by making a detailed comparison of these two approaches and points towards our conclusion. So I'll do the comparison in two parts. So in the first part, I'll be looking at the product of SU gauge groups. So here, if I assume that there is a non-trivial cyclic global quotient, so a non-trivial cyclic Zn gauge one form symmetry. And if I also take into account that the rank less than or equal to 18 unitarity bound, that comes from the paper by Kim, Xu, and Vafa, I will get the following conclusions. So first of all, for n greater than or equal to 7 being a power of prime, we get that all of the anomaly-free theories are realized via string theory. So in particular, for n equals to 7 or 8, there is respectively one stringy vacua according to the Shimada classification. And these are exactly the only cases that are allowed by our mixed anomaly constraint. And similarly, there are no anomaly-free theories for a power of prime between 9 and 19, which is consistent with the fact that in string theory, the cyclic order of torsion, the order of a cyclic torsion has to be no more than 8. Okay. So now instead, for the case of n being not a power of prime, we need to introduce a further assumption that Zn act faithfully on one simple Gi factor. So with the power of this assumption, we can also rule out all of such n's between 10 and 18. So there are no such anomaly-free theories, which is again consistent with the fact that there are no such stringy realized theories with such a high order of torsion. So another aspect is that we can also search for single factor gauge groups, but no longer restrict ourselves on SU types. So here, there are 10 cases that fits into 3 categories. So first of all, there are 3 cases that fits into the F theory on K3 category. And there's a second case, a second type with 5 cases that fits into AD CHL strings. And finally, there's a third case with 2 components that doesn't admit a non-string realization. So one might wonder that if they have to be ruled out by some other mechanism. Okay, so now let me come to our conclusion. So we have provided strong evidence for string universality for non-simply connected gauge group G mod Z in 8 dimensions. So in particular, we observe intricate patterns and restrictions regarding the global structure of gauge groups in AD string vacua. And this corresponds in the F theory context to patterns in the arithmetic structures of elliptic vibrations in F theory. And on the other hand, we derive the key supergravity constraint saying that the mixed anomaly between center one form symmetry and large gauge transformations of the B4 supergravity field should vanish. And in particular, we use this constraint to obtain a nice match with the arithmetic properties of elliptic K3 in the pure IN supergravity case. So exactly the same equation came up in 2 different contexts with completely different interpretations. And finally, we did a detailed comparison by this constraint. And with that, we can rule out a large family of apparently consistent ADN equals 1 theories with non-simply connected gauge groups that one cannot realize via string theory. Right. So finally, this points towards the string universality in AD. And finally, let me very briefly go through some of our future directions. So the first point is that one can seek for new insights into the global groups of AD-CHL strings and seek for explanations of the patterns observed there. There's also a recent paper that investigates the heterotic vacuum on torus systematically. So as a second point, one can see if incorporating the U1 factors can introduce, so they are known to be able to introduce new global quotients in the F-theory context, and one can seek for explanations in the field theory context, possibly via unfixing. And as our last point, one can try to compare this analysis with other swampland constraints. So in particular, there is the trivial cobordism conjecture as proposed in the paper by McNamara and Waffa, and later used in the Mordell and Waffa paper to look for string universality in dimension greater than 6 very recently. So in particular, in the Mordell and Waffa paper, had some results regarding non-simply connected gauge groups in AD, and their results are all consistent with ours. And that's all for my talk. Thank you for the attention, and questions are very welcome.
Great, Hal. Thanks a lot for the talk. Yes, if we can all show our appreciation for Hal's talk using our clap emoji, that would be great. We have a bunch of questions in the chat. Miguel, you
yes.
seem to come in first.
Hi.
Is it me? John,
yes, yeah, Miguel.
Yeah, okay. So thanks a lot for the very nice talk, Hal. I have a question about, so you explained that there are some CHL groups and you get constraints in the global form of the gauge group for the CHL string. So I just don't know any reference that discusses like the global structure of the gauge group of the CHL string in general. Like, do we know, for instance, that in CHL we can have SU8 over Z2, but not SU8 over Z4 or something like this? Where could I learn about this?
So there are no general references. So some of the references that I know involving the investigation of that thing from the string junction perspective. So,
okay.
So there one can demand some particular properties of the allowed strings at the presence of the non-trivial B2 torsion as opposed to trivial B2 torsion.
Okay.
And they give some examples, but there are no general treatments, and that is also what we are pushing for here.
Okay, if at some point, if you could like send me a reference over, I don't know, some way for because yeah, thanks.
Yeah, sure. Yeah, thanks for the great question.
Wadi?
Oh yeah, very nice talk. Very nice, nice results. It's very cool to see how this is fitting together. So I had one question really, which is, can you give us a little sense of the things which remain in the swampland? Like you mentioned that there's some condition you have to impose that like Zn acts faithfully for the smaller values of Zn. Are there specific examples or that you can mention, and how many of those are there where you don't have the Zn acting faithfully? Where there are anomaly-free theories that are not realized?
Yeah, so there are some cases. For example, if I take Z10 and I can somehow decompose into Z5 times Z2, well, Z5 acts on some simple factor and the Z2 acts on some other simple factor, and they can cancel like each individually such that the rank can not go above 18, something like that.
And if you just have one factor in your gauge group and some Z quotient, is there nothing in the swampland?
So there are the two cases at the bottom of the screen, which is SP12 mod Z2 and SP16 mod Z2 with no known realizations. And clearly their rank go beyond the CHL, and neither are they found in the Shimada catalog. So,
okay, cool. Nice talk.
Yeah, thank you for the great question.
Great. So Craig seems to be having internet connection issues. So with that, let's thank Hal again for his very nice talk, and we'll move on to our next speaker.
Yeah, thanks everyone.